quickly give a brief introduction to the first keynote speaker, James Howard Thompson. I know him for a long time. I was a PhD student at University of Wisconsin, and he was an undergraduate student there at that time. And then we see each other at different places on campus and whatnot. Then he did undergrad in electrical engineering, and then he did master's in electrical engineering. Then he went to the Bay Area to work for a year, I think. Then he came back to do PhD at Wisconsin. And so in 1991, he finished his PhD, I believe. So he had 6 job offers, as far as I remember, when he and I were chatting at the time. So he was like, being an engineer, looking at which one he's going to pick and whatnot. IBM was, of course, one of them, all of this. He said, I'm going to go to this small company called Qualcomm. So that's where he ended up being, and I know how big that small thing is now. So without saying anything more, I welcome Dr. James Howard Thompson.
So there is a story behind the title of this. So Deep asked me to do this talk about a year and a half ago, maybe even 2 years ago. And generally, I don't do talks like this. This is the first time I've ever been to an IEEE conference. Mostly, my career has been internal to Qualcomm. And so anyways, I agreed to do this. And then after I agreed to do this, Deep, he just kept calling different people at Qualcomm. Never me, but he kept calling different people at Qualcomm saying, we don't want Jim to talk about faster data rates for 5G. Don't talk about faster data rates for 5G. So anyways, this is a bit of a nod to Deep, and I'll try not to talk about faster data rates in 5G. But I will talk about 5G. But maybe to give you a little bit of background, if you look at our industry, going from analog cellular phones, and there's probably a handful of people here that have used the analog cellular phones. They were really horrible. The quality was really bad. Drop calls, capacity was really poor, so they're very, very expensive. And really, it was something that only rich people could afford. It's true. And even me, when I started working at Qualcomm, I could not afford a cellular phone. And then we started working on CDMA, and there's other work being done in the industry as well. And I think it was all focused on voice, and it was focused on voice capacity. And so we eventually, at least our CDMA system, went from, we originally were proposing, or saying we'd get about 20% or 20 times the capacity, and we ended up getting about 60. So it actually did meet the expectations that we had for it. And I think Qualcomm played a part, and a lot of people in this room, I think, played a part in bringing communications to the whole world. Now, I think today, the number of connections in the world is about 7 billion. So that's about how many people there are on the planet. So it's something that I think, I know I'm very proud that I've been part of that, and I think a lot of people in this room should be proud of that too. So some things changed, though. When we were working on CDMA, we also, some of you may remember that we had some software called Eudora, and it was an internal program that we did as an email client. And it ended up becoming the most popular email client in the world, and there are actually people that still use it today. It's really strange. Okay, there we go. There's people that still use it today. But I tell you that because at the time, our company was very plugged in with the internet. And so since we're very, very involved in that, at the very early stages, we recognized some kind of funny things that were being asked of us. Like for example, we're doing CDMA, and they said, can you implement analog fax over CDMA? Can you implement dial-up modem over CDMA? We're going, wait, this is a digital system. Why are we implementing some analog thing over this digital system? It's just digital, just use packet data. Well, anyways, because of that, we were inspired as a company to start pursuing data very early on. So that was probably the packet data. So, and EVDO, EVDV, for some of you maybe remember those terms. But so that was mid-90s that we started working on that. And then we started to think, okay, connecting to the internet, great, but what are you going to do with that on your phone? And we actually didn't really know, but we started working on digital camera. Remember, in the late 90s, that's when digital cameras were coming on. That's when MP3 was becoming popular. And so we worked on digital media and processing. And we actually developed an app store, believe it or not, I think it was around 2000 or so, maybe as late 90s. And so we did all these pieces, and we didn't know exactly what was going to come of it. But it ended up, at least those pieces ended up becoming what is the modern smartphone today. And so at the time, we felt like there's something really brewing here. We didn't know exactly, we're propeller head engineers, so we weren't maybe creative enough to come up with what exactly the smartphone looks like today. But all those technology pieces we started working on. So it was a very interesting time. So fast forward to today, we've been focused on smartphone for like now the last 15 years. And so now I feel like there's some changes going on because you look at 5G and some of the other things that are happening in the industry, artificial intelligence, Moore's Law has gotten to the point where you can integrate billions of transistors pretty efficiently onto a chip. So there's a lot of things that have been happening in the meantime that I think open up some possibilities. Okay, so I'm going to start, just what I'm going to talk about, start with just a very quick overview of 5G, talk about some of the use cases that I see happening and that we are pursuing within Qualcomm. We're trying to get some of these things going. And then also talk about 5G and how we might extend that in the future. And I'm just going to pick one specific area that at least I'm interested in, talk about how we might expand the capability of 5G, and then the importance of the wireless edge. And I think that's where I feel like things are changing pretty significantly. Okay, so 5G, just a quick overview. I think a lot of you know 5G is pretty heavily based off of 4G. 4G was focused on mobile broadband. And so if you look at what we tried to do, and because it was focused on mobile broadband, there's some, I would say, it's somewhat inflexible. And so providing other services on top of it has become a little bit difficult. And so that's part of what we want to do with 5G is expanding the capabilities so we can support these other types of services like mission critical services and also massive IoT. And then also opening up diverse spectrum. So there's a ton of spectrum at the higher bands that is available, and then also in millimeter wave. And it's about increasing capacity. So our goal is to increase the capacity by about 100 times. And if you increase the capacity by 100 times, and this has happened again and again and again, the price goes down per bit. And that's really what we want to do is we want to make data, ubiquitous data, very cheap. And then also supporting diverse deployments. Okay, these are just some of the foundations of 5G. So it's an OFDMA-based system, but it has scalable numerology. For 4G, you did not have, for example, when 4G was being developed, we were thinking more of lower frequencies and FDD. And at these lower frequencies, the tone spacing for OFDMA, you want that to be somewhat short because you have this very large delay spread that you can get in these macro base stations. And so having a narrow narrow tone spacing is important. But when you get to these higher frequencies, you end up with these smaller cell sites, and you don't need that. And so you can develop a more efficient system by spreading the tones out. And so within 5G, we support a wide range of tone spacing, and then also flexible slot structure. And the whole idea behind that is to provide some ability to build services on top of the slot structure that it's flexible enough to absorb these new types of services. If you look at 4G, it was somewhat rigid, and there were, there were issues with adding some of these features into 4G. And so what became the slot structure for 5G is really looking at 4G and what could we do better. And then, of course, improving the coding, going from turbo codes to LDBC codes. And then massive MIMO, I want to talk about this for a second. So massive MIMO, we had MIMO, of course, in 4G. What massive MIMO for 5G is it takes advantage of TDD. So it's really focused on TDD. With TDD, because your uplink and your downlink are in the same channel, you have reciprocity. And so the channel measurement that you make you can make it on the uplink applies to the downlink. So if you look at 4G, because it originally was done with FDD, that was not the case. And so in 4G, there was a lot of processing that had to be done in the handset, which made it somewhat impractical. Or we could support 4x4 MIMO, but supporting more layers than that became difficult. So with massive MIMO and using reciprocity, I'm expecting that we'll be able to support 32 or even 64 digital streams from a base station. So what that does is it gives you much more capacity, much better spectral density. And that's part of how we're going to get this massive increase in data capacity. Millimeter wave, I'm actually not going to talk about that today, but this afternoon at the CTO forum at 2 o'clock, I think it is, I'm going to talk about millimeter wave. Some of the practical challenges associated with it. Maybe the one thing I'll say about it is that millimeter wave is going to happen. It's going to work for mobile. Oop, yeah. Okay. So 5G, the focus for us is clearly we want to support mobile broadband, but we're looking at expanding to all these other types of use cases. And I want to talk about 3 specific ones as examples. One is extended reality and edge computing, and then auto safety, and then the factory of the future. Okay, these are, uh-oh, this is a problem. We got it? Okay. Okay, so I call these the, oh, this is not good. What do I do? Okay, I won't move. Okay. These are what I would call the Kingsman glasses. Have you guys seen the movie Kingsman? Okay, so it's a pretty cool movie, and they use augmented reality. So they have these glasses, and it provides all sorts of information, communications, all this. Well, that's actually possible. It really is possible. And this is what we're setting as our vision for the future when it comes to augmented reality. But we're working on, if you look at it today, like for example, we provide the chipset for Oculus Go. And for those of you at Oculus Go, it doesn't look like that. It's this big thing. It's an untethered, so it's wireless, untethered. All the processing is done in the headset. And it's really big. So, it's kind of this big weight on your face. But, I mean, kids love it. I've got one. I use it. Anyways, but if you look at from a processing point of view, like the Oculus Go, it's 2 megapixels per eye. But if you want to have virtual reality or augmented reality where you can't tell the difference between what's real and what's not, you need probably about 20 megapixels. So that's a factor of 10. Okay, so then when you look at Oculus Go, this big thing, and you compare that to these glasses, it's probably another factor of 10 in terms of size. So when you think about the kind of performance that you need in these devices to be standalone, it's pretty high. So you're talking about a factor of 100 maybe in terms of power per performance. So that's a pretty big challenge. Now there's a lot of things that we can do to improve that. One of the things that we are looking at is, can we offload some of the computation using 5G? Remember, 5G is very low latency, so 5G has about, can support less than a millisecond of latency. So can you offload some of the computation for something like virtual reality or augmented reality? And we've been working on that, And the answer is yes. And I'll talk a little bit about how this works and how you compensate for motion and things like that. But, okay, so very simple. You're standing there, you're looking somewhere, and there are sensors on board that measure your pose. And there are 6 degrees of freedom. You know, you can move, walk around, rotate your head. Okay, so here's the catch, is that if you move your head and the scene doesn't move with you, so that you go like this and then the scene goes like this, you're going to get sick. I mean, it's really very uncomfortable. And so you have to have something like, 10 to 20 millisecond photon to motion latency, or I should say motion to photon latency. So that's what you need to make it comfortable. And so what we do is, with using this millisecond latency over the air link, you can then do the frame processing, most of the frame processing, but it's still not quite good enough, because a couple things. One is, you don't necessarily want to put a server at every base station, right? You want to have it back in the network, so that you have to be able to absorb a little bit of latency. And so what we do is what we call time warping. So what we do is we have the server predicts where the user will be looking, but they're not going to get it quite right. And so what we do is then do the final render on the device. So you see, we end up splitting the rendering, where we do an approximate rendering in the cloud, or in the edge cloud, and then we do the final rendering on device. And I want to point out, and maybe this is obvious, but doing something like this in the cloud is probably not practical. When I say in the cloud, meaning 100 milliseconds away, it's probably not practical if you think of like roughly how far away the cloud is. So anyways, that's an example. It's very early on. Like I said, I think the ultimate prize is augmented reality and those little glasses, but this is one of the steps to get there. Okay, autonomous driving. Everybody has heard, you've read in the newspaper. When you read it in the newspaper every day, you know it's maybe a little overhyped. One of the things I want to say about autonomous driving is that I think really the prize in autonomous driving is not the convenience of somebody else driving the car, or a machine driving the car for you, but it's safety. So if you look at worldwide, about I think it's 1.3 billion people die from car accidents every year, which is an amazing number, actually. And if you look at, take, for example, lung cancer, which is a death sentence, that's roughly how many people die from lung cancer. And so imagine you came out with some kind of cure that helped, let's say, 50% of those people, we cured 50% of the people from lung cancer. And you would be you get a Nobel Prize, right? But that's the opportunity that we have in front of us with autonomous driving. And so I'll just talk about a few things related to this. This is something that we're working on. So the sensors that I think are most important are vision, radar, positioning, and CV2X. So I won't spend a lot of time here on vision and radar, although there's a lot that can be done with that. In particular, radar. I'm very, very excited about how well you can use radar. But let's just talk about CV2X for just briefly. So CV2X is something, so it's cellular vehicle to vehicle to network, vehicle to pedestrian. So it's something that Ed Tiedemann from Qualcomm is going to talk about at 2 o'clock tomorrow. So he'll go over in great detail. But think of it as a way for peer-to-peer communication between cars, so that you know the intent of the cars. And you can actually even understand, if there's sensor data that they can deliver over. So it provides a peer-to-peer, a secure peer-to-peer communication that allows cars to understand the intent of the other cars. Okay, so understanding the intent of the car doesn't matter unless you know exactly where it is, and that goes to precise positioning. So if you just use GPS, actually GPS is not very precise because it's subject to multipath, which can make you miss by hundreds of feet, hundreds of yards even. So multipath can really make your position location off. And even if you don't have multipath, there's ionospheric effects and things like that. And so there's a bunch of things that can be done, and by using the odometry that you have on board of the car, and then also using your camera information. So we call it visual inertial odometry. So you can correct GPS to be within about 10 centimeters. And that's definitely accurate enough. Maybe a meter is accurate enough. So anyways, there's a lot of work going into that. And the combination of those two things, along with HD maps. And so what you'll get are, in whatever region you're in, you'll get HD maps. They'll be downloaded from the network. And then that will aid in you understanding, or your car understanding, what everyone else is doing on the road. So those are very important elements. And I'm going to use this example later on in the talk. And so I'll stop here. Okay, factory of the future. So factories have lots of wires and cables everywhere, and they would actually like to go wireless. But I showed this video, this brief video, to give you an idea of how dynamic that environment is. So, it's very cluttered. So from an RF point of view, lots of multipath, scattering. You have things that move very fast. So you have these robots that are moving around, causing changes in the channel conditions. And so one of the things we look at is how, from a reliability point of view, that's something that we're spending a lot of time trying to understand. And also latency. And obviously, if you have infinite amount of time, you can make it super reliable, right? So, but you don't have infinite amount of time. In fact, and I'll just use one example here. We're looking at an Ethernet replacement. So Ethernet replacement, it may require, we think of it in terms of 6 nines of reliability. So it's very reliable. And then also it needs to happen within less than 1 millisecond of latency. So anyway, so there's pretty difficult requirements, and I will come back to this one in just a second. Okay, because it's related. The solutions to those things are related to comp. Sorry. Okay. So how do we extend what we have in 5G? And one of the areas that's very interesting to me is coordinated multipoint, as well as spectrum sharing. So what I want to talk about first is what is the difference between coordinated multipoint and massive MIMO? And the answer is not a lot, but if you look at massive MIMO, the way people think about it is all the antennas are at a base station. And let's say, again, there may be 32 digital streams and antennas, 64. That's the kind of number of antennas we're talking about. And then in order to get MIMO, so you have a device like this, and you want to be able to separate antennas on that device, you need to have multipath. Because if you're really far away from the base station, it's not going to work. You're going to just get a big beam, and it's going to cover the whole phone. So the only way this actually works is you have to take advantage of multipath. And it actually does work very well. Today, networks support 4x4 MIMO, and it actually works really well. That's in LTE. Okay, but again, you have to have multipath. So now if we go over to the right side, and I like to call comp distributed MIMO because it's a little more descriptive. But think about, instead of antennas in the center, the simplest way to think about it is all the antennas on the outside looking in. So it's just different in that way. And then because of that, you don't actually need MIMO. You don't actually need multipath to make MIMO work. So it's a very interesting concept. It's been around, by the way, in the academic world, it's been around for a little while. But I think we're at the point where we can actually use it. And maybe just a quick overview of what it is. So you think about if you're going to serve 2 users in a network. This is a distributed MIMO system. So look at the blue phone. So we're transmitting to the blue phone, sending data. And then what we're doing is we're steering a null. So there's a peak to the blue phone and a null to the green phone. And that's what the dotted lines are. And then at the same time, we're steering a signal to the green phone because we protected it with the blue null. And we're steering a null towards the blue phone. So that's basic concept. This is very simple 2x2 case. But if you have, let's say, 32 antennas, you can support up to 32 phones, digital streams, and you can protect them as well. Now, it requires, practically speaking, you always end up with less just because of the channel conditions. But that's the basic idea behind this. And so one question is how can you deploy this in a macro system? Because you can't have an infinite number of coherent antennas. You know, you can't cover all of Kansas City with one essentially massive distributed MIMO. Okay, so let's look at, we've got in a one-dimensional case, we have two clusters, I'll call them clusters, of coherent antennas that are around each other. And imagine a cluster of antennas might be a couple hundred yards or 500 yards or something like that, just to give you some physical feel for it. Now, these two are operating next to each other, but you can imagine, just like in any cellular system, you have interference at the edge, the cell edge. Okay. In 5G, we have something called the sounding reference signal. So what that does is it allows the adjacent cluster to actually listen without any information. It can listen, and if it hears a sounding reference signal from one of the adjacent clusters, it knows that if that phone can hear, or the cluster can hear the phone will be able to hear potentially the cluster next door. And so therefore, it's incumbent upon that adjacent cluster to provide protection, so to steer a null. So there are, given the number of antennas you have a certain number of spatial dimensions. So if you have n antennas, n spatial dimensions, and you have to steer one of those, essentially using one of those dimensions to protect an adjacent cluster. Okay. That's a concept, and I'll get back to that. Okay, now I want to talk about spectrum sharing before I combine the two, distributed MIMO plus spectrum sharing. But I want to talk about where we are today with spectrum sharing. So everybody's very familiar with Wi-Fi. I'm sure there's people in the room using Wi-Fi. And the way Wi-Fi works is it's listen before talk, which is, so in other words, it's respectful of other users. If somebody else is on, you don't jump over top and use the channel. You wait until it's your turn, and there's some protocols associated with that. And that works fantastic, especially when there's nobody else using it. Fantastic. You get the whole bandwidth. The problem with it, and anybody has been, like I'm a Packer fan, I went to the Super Bowl. You go to the Super Bowl, it's a disaster. It doesn't work. And so what happens is when you get too many people all vying for the channel at the same time with a listen before talk, there is no quality of service. So there's nothing that protects the quality of service. Okay, if you look at spectrum sharing today with 4G, we have, we support license-assisted access, we call it. So you can support LTE channels, and this has been deployed in unlicensed spectrum. So in the 5 gigahertz spectrum, it has been deployed in the United States, and I'm not sure where else, but it certainly has been deployed in the United States. And that's when you see some advertisement for gigabit LTE, that's how they're doing it. Okay, but again, well, maybe I'll make one quick comment. License-assisted access is actually a little bit friendlier to Wi-Fi than Wi-Fi is to itself. Qualcomm does a lot of work in Wi-Fi, so we're very, we're very concerned about the quality of Wi-Fi as well. But anyways, LTE in unlicensed spectrum works very well. Okay, So now, this is a very simple concept here that I want to introduce before I go to the next slide. And that's, if you're going to share spectrum, today what they do is you, at least in the license band, someone will buy some frequencies and then another company buys another set of frequencies, and you don't share your spectrum. So I think a better way to do that, and I think this also applies to unlicensed spectrum as well, but a better way to do that is time division multiplexing of the channel. And I'll explain why that's important. And this is super simple concept. If operator A and operator B are sharing, you're just splitting the time. And then if operator A, for example, finds it doesn't have any traffic to serve, operator B can jump in there either through a listen before talk mechanism, or there's some kind of coordination between the operators. Active or passive coordination. Okay, so now let's take the example that I gave of the same operator and adjacent clusters. Remember, so the adjacent cluster, there's a mechanism in 5G that allows that adjacent cluster to manage the interference of the other cluster, okay? So let's, so just to make it clear, these are operators, two different operators occupying the same physical space. So it doesn't necessarily mean their antennas are in the same towers or anything like that. It's arbitrary, okay? Okay, so we have the same situation where operator, A and B are sharing in time. So think of it as operator A in the blue there is the primary when it's blue, and B is the primary when it's green. And then how do you opportunistically share if you're not using all the capacity that's required? And so there's that mechanism that I talked about. If nobody's using it, then the second operator, operator B, can jump in. But when you're using comp, you can now share actually the time slot. So imagine in this case, operator A is not using all of the spatial dimensions that he can. So in other words, his capacity is based on the number of spatial dimensions, the number of antennas that operator has in that location, not using them all. And so, and this is kind of the crazy part, is that operator B can actually, they don't have to be told that he's not using all the spatial dimensions. So operator B just listens and goes, oh, I see a sounding reference signal here, here, here. In this case, it's just one. I'm just showing one. But can listen for all the sounding reference signals and know that that other operator is going to service those customers. And then as long as operator B can protect operator A's primary users, then operator B can go ahead and use additional spatial dimensions and run right over the top, and with very little interference impacts. So it's really kind of interesting. Now there's two different ways of doing this. One I would call the polite way, and then there's the impolite way. So the impolite way is where the primary operator just does whatever he's going to do, and operator B just is hovering over the top and doing, servicing his customers. And then there's always a chance that operator A will interfere with operator B, because the operator A doesn't know anything about what's going on with operator B necessarily. Now you can change that protocol so that you make operator A operate politely. And politely is, I know I'm sharing the spectrum, even though I'm the primary, I am going to make a measurement and then protect the users of operator B with the extra spatial dimensions. So, and that's something that we're looking at and trying to understand what the best way to do this. And so that may involve some additional protocols. But I think this is something that has got a lot of promise for spectrum sharing. And I'll just show you. We've been working on this in our lab. The upper right is we have this big warehouse, and there's a lot of chairs and desks and stuff like that in it. But we also use it as a test bed. And we have two operators in that facility or to operate. We're the operator, so we're just testing it. And we've shown some really, really good results using this. And if you look on the left side, and this kind of gives you a feel for how the spatial dimensions and how well you can form these nulls using a system like this. These are actually 4 5G phones, and here we're only putting 2 antennas on each one of these phones. They're stacked on top of each other, yet we're delivering the full bandwidth to all of them from 2 different operators. So I think it's really got a lot of possibilities, and that's why I wanted to present it, because it's something that kind of is very interesting to me. Okay, so I'm going to step back and go back to MIMO, distributed MIMO. And remember that example of factory floor where everything was moving around and things are really cluttered? The problem we have is in the factory, it's a very dynamic, 5 minutes? Is it at 35 right now? Okay. Okay. So in order to get 6 nines, you have inherent diversity within this distributed MIMO system. But to get 6 nines, you're going to need more diversity than that. And so we're looking at things like frequency diversity, antenna diversity, and there's even some level of time diversity with hybrid ARQ, retransmissions that can be done within 5G. And it all comes down to the time required to do this. So like I said, for Ethernet, it might be less than a millisecond. And so you're limited in how many retransmissions that you can do. So really, I think you're going to need likely antenna diversity. So think of it as taking MIMO and using some of the dimensions to provide a reliability. So you're giving up capacity for reliability. Okay. Okay. This is, I know I got 5 minutes left. So this is the wireless edge. Okay. This is something that I've been thinking about, and I'm sure there's probably going to be a lot of people that disagree with me. But anyways, okay. So today, you look at AI, deep learning. It's really happening in the cloud. Obviously, it's used in a lot of places, but like, where is it really happening and making a difference? Where is it being used commercially? It's in the cloud. And you look at like what's being done by Googles and Facebooks and others, really remarkable. I mean, some of the tools, TensorFlow, PyTorch and Cafe2 and others. There are a lot of different tools around the world, but they're really, really amazing tools and allowing engineers to solve certain types of problems that they couldn't solve before, or very, very, very difficult. But you look at today, and why is it all happening in the cloud? It's because that's where the data is. Okay, so if you look at what is the data? It's mostly social media. So it's like search. You type in for search, or you upload pictures or whatever. So it's mostly because that's where the data is. But then, and what is it used for? It's mainly used for advertising and trying to get you to buy stuff, and which is good, all good, and that's paying for everything. So that's awesome. But I think in the future, I think that this is something that's going to be super important at the edge of the network. And you look at, like, for example, that example I gave you with driver safety. The way I see this working is that I don't believe for a second that the inferences that are done are going to be done in the cloud. So in other words, if you're looking at a traffic situation, if anybody's watched YouTube Russia dash cam, oh my God, it's amazing. And it gives you an idea of what crazy things happen with traffic accidents. And so the inference, there's no way you're going to wait 100 milliseconds for the cloud to do an inference for you. And so no matter how reliable the 5G connection is, you're not going to rely on that. Okay, you got to have other things. You got to make the local decision. So how do I see this happening? Well, I think still the trained models are going to come from the cloud. That's just the natural place to do the training because it's super complex, a lot of processing required. But when you think of the car case, driving in a car, most of the time when you're driving, you can even forget your whole drive, right? Because it's just mundane. You don't remember what happened because nothing unusual happened, nothing out of your experience happened, and that's what we call super low entropy data. All that data you collected, which, by the way, from our test cars, it's over a gigabit per second, is useless. Okay, 2 minutes. Okay. Now Deep threw me off. Sorry. So what you really want to do is you want to analyze that data on the automobile, understand what the high entropy data is, and then deliver that back to the cloud. And what you're going to see is the different auto companies like General Motors, for example, will have their own system where what they'll do is they'll be monitoring you, and there's going to be a privacy question there. But they'll want to capture all of that crazy data. Like when you get into an accident or something crazy happens on the road, that's what they want. And getting that data is going to be very, very difficult. I'll say one more thing about processing at the edge. And because deep neural networks, it's a different kind of processing. Like, for example, a CPU, if you run some of these neural networks, it's very, very poor at processing neural networks. And so what you're going to see, and what at least at Qualcomm we're working on, is dedicated engines for neural processing that will run, between 50 and 100 times more power efficient, or I should say energy per inference efficient, than you have in a CPU or a GPU as well, much more efficient than a GPU as well. And I think this is something that's super important, an important research area. And on top of that, these neural networks, when you train them in the cloud, they can be very, very large. And another area of study that I think is really important is how do we compact these neural networks down and maintain the relevant information. And we've done some of the studies in different cases. We've been able to reduce these inference engine networks down by a factor of 10 or even 100. So when you think about, let's say you get 100 times better performance from the hardware, and then you get another 100 times performance by compressing the network. And then you're talking about some really amazing capability that you can bring to the edge where power matters. Maybe I'll stop right there. I think I'm getting the high sign to get out. So.
Well, thank you so much for the talk. So the first question is that, what do you think will be the first killer applications for 5G?
First applications for 5G, okay. Very clear. It's being deployed in 19. And right now, the initial deployments, what I would say in 19 and 20, are really going to be about mobile broadband. So you have operators that want to expand capacity in their networks. So you're going to see in 19 that, like in the US, there'll be millimeter wave deployments. And they'll actually, I'll talk about this afternoon, but actually the coverage, if you just stick millimeter wave and base station at existing cell sites, you actually get pretty good coverage in some of the dense cities. So I think you're going to see that. But really initially it's about increasing capacity dramatically for mobile broadband. And then some of these other things I talked about, I think will happen later on.
So the second question is that LAA, the licensed assistant access, is more efficient than Wi-Fi in some only corner scenarios. It has lots of drawbacks. So why not considering the latest advantages of Wi-Fi, like such as 11ax?
Yeah. Oh, yeah. So we sometimes people think that Qualcomm is against Wi-Fi, and it's absolutely not the case. We're actually the leader in Wi-Fi. I'm pretty sure we sell more Wi-Fi than anybody else in the world. So we do both. 11ax clearly is something that we're promoting and we're working on. But unlicensed spectrum is used for different things. And it's clearly it's going to be used for 11AX and AC today. But operators, you look at like Verizon and AT&T and T-Mo, and at least in the United States, Sprint, they can use that spectrum as well as long as they're a good neighbor. And so I think it's good for that type of sharing.
Thank you. So the next question is, what do you think is the biggest challenge in commercial deployment of 5G network?
Okay, so the biggest challenge of deploying 5G is just this is the first time, just back up. If you look at 4G, when that was deployed, it was FDD, the feature set was pretty narrow, and it was, we understood what that was. If you look at the deployment that we have today in 5G, there's millimeter wave, which has a lot of challenges, practical challenges. But then on top of that, you have TDD deployments I talked about in the 3.5 to 4 gigahertz kind of range. And then we also have FDD deployments for operators that would be in like the 600 megahertz range. And what they're thinking there is they want super broad coverage through that. And so the point there is that it's almost like we're doing 3 systems in one. And then even a subtlety there is some operators are choosing what we call standalone, meaning they're using the 5G core network, and some are choosing to use the 4G core network, and we call that non-standalone. So there's all these different variations of the network. And so for a company like Qualcomm that we try to deploy everywhere in the world all at once, it's really challenging. So.
Thank you so much.
Yeah,
Thank you.
Thanks.